So I'm happy to see you on this last session. So I'm so happy that you are with us till the end. And we will talk about implementation of machine learning project on Zebra device. My name is Rafal Firlejczyk. I'm working as a sales engineer out of Switzerland. I graduated in 90s from Warsaw Technical University. Then we moved to Switzerland, and since 11 years I'm working for Zebra Technologies in Switzerland. 5 years ago I had to go back to school, so I graduated from postgraduate studies at ETH, this is Swiss Federal School, doing computer science 2 years courses with the focus on machine learning and wearable computing. So if we talk about Zebra newest Android devices, you need to know, or you definitely already heard, that we built it on the Qualcomm newest enterprise chip, which is called Snapdragon 660. And meanwhile, this system-on-chip device has become a standard platform for us. Newest devices like TC52, TC57, 72, 77, MC93, 83, TC83, and the newest EC30, even other devices are built on that chip. So I think it's worth to think about it and to talk a little bit about it. This project, which I am going to talk, will be implementing using Tensorflow Framework from Google and Snapdragon Neural Processing Engine from Qualcomm. But why do we care? Why do we care about it, that we have a newest chip? Just look at this Gartner research telling that in 3 years from now, most of our mobile devices will be shipped with on-device hardware components which will unlock the artificial intelligence direct on the device. So from 10% in 2017 up to 80% in 3 years from now. Why? Because running machine learning, or a special part of machine learning called inference, direct on the device brings you privacy, reliability, low latency, and very efficient use of the network. Now, let us dig into these devices a bit and check what we can, how can we use these new capabilities. So this is the agenda of my talk. We will start from short introduction to ML. There were today and yesterday several very good talks about machine learning, so I will assume I will make it shorter, not to repeat the things. And my goal here is not to teach you the machine learning, just to discuss a little practical things which are maybe important for you when you start to work on it. Then we will talk shortly about development environment of machine learning project and software tools which we have to do the job simpler, like for example Tensorflow. And I'm going to introduce you, of course, to our Snapdragon 660, and in the end we will talk in detail about this project which we've implemented, and finally about the achieved performance, because this is the key why we are using it. So let's start by defining what machine learning is and how it differs from normal programming. So the biggest change here is the way how to get the solution. So let's start to analyze the human activity detection task, like laying, sitting, walking, running, and so on, in the standard approach and in the machine learning approach. In the standard approach, you will get your data coming from sensors like accelerometer, gyroscope, thermometer, maybe camera. And then you will yourself look at this and say, okay, this guy must be sitting or laying because the accelerometer is showing nothing, or these axes are like this. When he's running, you will see that accelerometer is really showing you much of the movement. And then you will say, okay, these are thresholds for running, these are thresholds for sitting, and you yourself have to do it. You have to do it, you have to find the formulas and implement them in this observation in program. This is so-called hand engineering. And in the machine learning approach, which is the right picture, the programmer will just construct an algorithm and deliver the data. And the algorithm itself will construct these formulas for you. So this is this magic which is coming, and these formulas will be taken because you deliver the data and you know what the data means. And in that situation, the machine learning, when you look at this graph, will provide the model which will transfer this input data, which are coming, into the output result. And this is what is it about. But how to decide which approach should we or should you go? So below you have a few questions which will help to decide. But the most important thing is in the beginning, remember, machine learning approach is complex. So try first to solve your task with this standard approach. So using your own engineering skills and you are expert in, you could develop your standard app. You will keep it really simple in the beginning. Sometimes, however, this standard approach does not bring you the solution, or it's not easy. And then you may try to change the approach to machine learning. You have to answer all these questions to yes when you want to approach this way. So do you have existing and valid data set for training and validation? What does it mean? You train your network now, or you train it 1 year ago, and then the production will be maybe in 6 months or maybe in 2 months. Maybe the data set which you get now will be not the identical than the data you will receive for the real production. What happened then? You cannot really make a good program if you deliver other data in the beginning for train your model, and then test it in the different data set. Then, do you have enough data? You need to have quite a lot of data. Meanwhile, this problem is slowly not that difficult because many companies are delivering data now, our devices as well. Then, important thing, do you have enabled hardware for training? You need to have a cloud or hardware to train your model. And, of course, on the device, you need also a kind of fast elements which will compute for you. And last but not least, do you have people who want to go with you and know what is a little bit about data science, about programming, about machine learning? These are the questions which you have to somehow, as a leader, as a project leader, answer as yes, or at least have a good idea about it. And to go to the details, I will now introduce you to these 2 small projects which we did on our devices. And the first one is the object recognition project. Our task is here to classify, let's say, 7 types of Zebra devices. Some of them are here to show. You know how these devices look like using the camera of the device. So program should analyze the image coming from the camera and correctly classify it. So this is the task. When you think about this task, recognizing images using standard approach maybe would be possible, but very difficult, because how to find the difference, for example, between TC51 and TC75? And even if you find the optical differences, there are some optical differences, what will happen if this device change the position or move to another area of the image? Will these static formulas work? I don't think so, that it will work very good. So therefore, we've chosen the ML approach. And this project was done to justify, is it working or is it not working? And the second project was pretty much the same, but it was the teamwork with my colleagues Sean and Jing from New York. We like to automatically evaluate the quality of the image, so taken by the camera of our TC device. Like here, you have one picture, one image which is of good quality, one which is blurred, and one which is noisy. The use case is, for example, the image can be used by the proof of delivery, and it should be of good quality to be able to read the labels. And you know how it may happen that this delivery agent, they are always in a hurry, and maybe the light conditions are also not that good, what provokes that the image can be blurred or can be noisy, whatever. And the idea, the use case is that just after taking the picture, the agent gets the feedback, good or should be retaken. Huh? So this is the small think about it. We could also use here the classical approach, but then you have to apply filters. You have to decide from which point you think this is going to be a good, from which point it's blurred or noisy. And another thing, we wanted to use the knowledge we gained from another project and transfer this learning to this project to see how it works and if it's worth really to well document everything, to have some basic data, and then just within 2-3 hours to have another case done because we know already the models and we know everything. But please think about possible project or use case you may have, and you can see white cards which are evenly distributed. When you have time, please go to this survey and tell us what you think about machine learning, what projects you may have. We will try to help. So, okay, we have our projects and how to start and how to proceed. Structure, as you see, of the machine learning project is not that simple. In our case, we can describe it with these 11 boxes. And first 2 boxes, gathering and preparing data, are, let's say, almost the most important and may take 80% of your time. And so gathering data, we need to guarantee that we have enough good quality data. So if your task is very simple classification, you get the data, for example, from sensors like accelerometer, camera, gyroscope, microphone. You need to collect it, save it somewhere, and label. What does it mean, label? You have to decide, is it, let's say, this class or not? And then you have like your data and your true data. And this is very important. So this is labeling means that you're classifying the training data based on chosen features. And this is, of course, a part of so-called supervised learning. And in the case we have to gather a lot of images. The more you can gather, the better it is. And the rule of thumb number 1 is try to collect equal number of the images of each class to have balanced data. I think 1 hour ago, Vicky also told about it. And then you have the balanced data set. Rule number 2, the more complex model, which we'll talk later, is the more training data you need, because there are so many possibilities that you can very easily come to so-called overfitting, where the model is exactly mirroring your data without generalization, what is the most important thing in model tuning. And then the third important thing is the more good quality clean data you get, the better model you will receive. It's of course, it's obvious. And then you have to prepare the data. What does it mean? You get the data, you have to clean it, you have to normalize it. By normalizing, I mean you get, for example, data coming from a gyroscope or from accelerometer, starting from -100 to +100, and doing like this. Then you have data from temperature, which is coming from -10 to +30. Then you have another data, maybe 10,000 to 1 million. If you put this data into the model, it will never train good. So you have to normalize. You have to give like common sense. And the good common sense means you give this data, they can move, for example, from 0 to 1, each of them. And then they will be good accepted by the model. And then, of course, you have to mix the data, split this data. The data you will use only for the training and the data for the validation. Data for the validation will never be shown to the model for the training. It's our check. I'm checking you. You never saw it. Tell me what it is. So this is the idea. You cannot mix it. And normally all the procedures, all scripts are doing it for you automatically. Then very important thing is model selection. It is normally the machine learning expert choosing the range of the model he thinks would be good. There is another way, AutoML, which is very active. People are now in Google very active to do it, but it's not time to tell it. It's the situation that there is an algorithm which is automatically choosing and swapping models and telling, okay, this is better, let's put it on that way. We are talking about the machine, about the manual models. And you, if the task is relatively simple, you may check first your own models, you think. And there is quite a big number, like Bayesian, random forest, KNN, you name it, regression, and so on. However, for the complex task like image recognition, it's better to check first the publications and papers. Chances that you find yourself optimal model based on trying are relatively low. So especially for the image recognition, the best results could be achieved with a deep network, especially with a convolutional neural network. And the convolution is the way to automatically extract features from the objects in the image, which can be then used for distinguishing from object. And convolution makes also another very important thing. It makes this recognition immune for the position of the object in the image. So even if the object is here or here, it will see it. You can imagine that sometimes this finding even the object in the image can be a difficult task. So next three boxes like training, evaluation, and parameter tuning can be discussed together because they are connected in this iterative loop. I want to say that very good results now can be also used by using pre-trained models. There is a library of many pre-trained models and just retraining it to customizing it. And this method is called transfer learning. And training or retraining starts normally by inputting this data, this shuffled data we have, and then we calculate the response error in this forward phase. Then we do the backward propagation to calculate how much should we tune these parameters, and then over and over again, 10 million times longer, until we're happy. That's the idea. So after defined number of these so-called epochs, epochs is when all your data is once in training. That's one epoch. So if you have 1 million pictures in the training, after 1 million of this iteration, you have one epoch. So after several well-defined epochs, you can transfer this, you can stop the training and say, okay, now I will give you the data set for the validation. And then you check, this data was never seen, so let's check the model. And having this done, we may decide, is it good enough, this is what our project wanted, or we have to tune another so-called hyperparameters, which are outside of the model, like learning rate, number of iteration, and so on. And then you already see that this activity is very, very, very long-lasting and boring. So, And sometimes even, you have chosen the model and you say, no, this model doesn't work. That's why you have here this dotted line. You go back and you say, no, this model was not good. Let's try with another one. And do it over again. But if you are happy with this, you can come to this lower part. So as a result of this previous step, we have our model. And now we need to get it out of the training program and make it available for our device. And all boxes here in the green are showing the activities which are done on the device. The upper in a blue are normally done on a server or in the cloud, like Savannah, like Google, and any others. How to take this model from the training program? It means to take the model, you have to save it to the file, as easy as it is. What do you save? You save the graph, so you save the architecture, and you save parameters which you trained. And all this process is called freezing the model. When you read any documentation, freezing model is just setting, deciding, okay, this is the snapshot of model I want to have. And then in our case, we will freeze the structure of the model and tune values which will be the weights and biases. And then we have to use conversion tool from Qualcomm to convert it from a TensorFlow model to a Qualcomm custom model, which have a so-called DLC model. Especially DLC quantized model is important because it uses so-called 8-bit precision numbers. And it can be then run on the DSP, which we see afterwards. And now this small about this, a little bit about this application development part. It's normal Android application with the integrated APIs, SNPE Java APIs, and you can enjoy this prediction on your device. We will talk about it a little bit later after I introduce you to Snapdragon 660. But for the moment, let us go back to the project to check how we are going to follow our process. So this is the Qualcomm slide defining the same process which we discussed already. And we have, in our case, two types of images, training data and test data. And as mentioned before, we will collect them, label them, and we will choose one of the best convolutional neural network model built by the data science from Google for the recognition. And for the simplicity, we will use already pre-trained model. And then we will retrain it to tune to our images. When the model is good enough, we will freeze its weight, convert to the DLC model and DLC quantized, and transfer to the mobile device. Sounds like plan. Huh? So first, gathering and preparing data. For project one, I have to collect many images of our devices. It's not easy to find. So normally you have 10 images of each device in internet, or you have to do it yourself. So what I did, I took a small video of these devices, and then I used the program to cut off frames. So the idea was to move around the device, to show it from the different angle, in the different light conditions, on a different background, to make it more representative. I think it's a little bit cheating, but I do it. I don't have another way to get more these pictures. And I did it the same for the 7 classes. You can see here that I prepared the data set and I put the data into the folders of DS36 up to ZD500. It was about between 100 and 300 images per class. The same thing for project 2, where we wanted to distinguish between good quality, blurred, and noisy pictures. And imagine, it's even more difficult. You can find millions of good pictures, but try to find million noisy and million blurred pictures. Nobody's saving them. So what you can do, you have to collect normal, very good quality pictures and cheat again. Huh? You have a software, MATLAB, where you can say, okay, please add noise. So do distortion. So this is the way which Shan was doing. She was giving lots white noise, this noise, and several noise. And then you can also take a point and make it blur. Everything in software. So this is the idea. And then we deleted corrupted images, mixed them, resized to fit to the model. As you cannot see here, but we had 1,000 identical images. Good one, blurred one, and noisy. And they were the data set we used. And then a little busy slide, but don't worry, I will explain very shortly. So this is the Inception V3 model developed by Google Brain Team. It is a convolutional neural network, 42 layers deep. So normally you will never do it without really being a professor of mathematician and so on. And even more difficult, it is trained on more than 1 million images. So million compared to 2,000, you better go for million. And they are divided into 1,000 classes, and each class, like dog, cat, apple, has something like a few thousand of images. So you can imagine how good and how long will it take. And please take a look also at this input. We have as an input 299 by 299 pixel resolution with 3 colors. So this is the picture we have as an input, and after passing through this model, this array is becoming 8 by 8 only. So it's like flattened, but the other resolution, the other dimension, is not more than 3. It's 2048, and this 2048, these are our values which the model, which are encoding crucial elements of each object. So they are called so-called bottlenecks. In practice, very few people are able and will train such a convolution network from scratch, because it's expensive, takes days, and it's rare to get enough data to do that. So we are using here in our pre-trained network, and it is a good way to solve the most of these problems. And important, we will train only last 2 layers located here in the end, where this magnifying glass is. The rest will stay intact, and it means that instead of millions of parameters, we will have only 1,000 to do. And this is the idea of so-called transfer learning. It means that most of the knowledge learned somewhere in the Google Cloud will be transferred to my device. Cool, isn't it? So now let's see how these 2 layers look like. Sorry for the graph, I made it myself, so the lines are not that perfect. But you can see that these 2 layers are called, the first one is called bottleneck, is 2048 nodes, and the other one is the softmax decision, it's output layer. And when you pass the images through the network, the first thing the script will do will delete all the old values. It means we want to start from the beginning. And then it starts to calculate only this data, only these nodes, because the rest is frozen and become frozen. And as you can see, there are 2048 of these dots, and each one represents and then there are 7 output nodes. Each one represents 1 device in project 1. So there will be like TC 51, 71, 75, blah, 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 and up to. And in the project 2, there will be only 3 dots. So good, blurred, and noisy. It means, because they are fully connected, that you have something like 14,000 values to calculate in project 1 and about 6,000 in project 2. And then it takes about 20 minutes to do it. And as you can see, today nobody would program the process of generating models in the low-level programming language. To make it possible, there are on the market several machine learning frameworks which abstract for you the low-level programming and make it easier to design the model and then train and then also debug. I've chosen the Tensorflow. It's a machine learning framework developed by Google Brain team. And there are three important characteristics of this model. It's an open source. It's very important. It's possible to run it on a different hardware in the cloud, mobile devices, IoT devices, Raspberry Pi, and so on. And it's possible also to run it on several servers. So you can distribute the calculation to make it faster. And before, the history is that it's the architecture. It started as a just numerical computation library with a focus on deep learning, but with the time it evolved and get more and more collection of machine learning algorithms. And as I told you already, the engine can work on many different hardware, IoT, our devices, Android, and so on. And you can program with lower APIs using C++, using Python, using Go, and then you can train from scratch, or you can use the upper layer and then use this canned or estimated or Keras model, and then it's a few line of codes because it's abstracted. And especially Keras, please remember, Keras, it's become the most important upper layer, starting from TensorFlow 2.0, so from April 2019. I used for the retraining a Python script called retrain, which is part of the TensorFlow for Poets tutorial. So now we have our train model, and we should now transfer the model to the hardware. But before we do it, let us get know a little bit the hardware we have in US Zebra devices. So Snapdragon 660 consists of three important computing elements. CPU with 8 cores built in so-called big little. So 4 cores big and 4 cores small. They never work together. They have but if you need for our calculation, of course, the 4 big cores will be working. And then we have GPU Adreno, which is important, and DSP Hexagon 680. It's a vector processor. So important that we have 3 separate hardware components on which we can run our inference. And here is the slide also from Qualcomm showing that they are delivering not only this hardware but also all around, like support for TensorFlow and Caffe important. You should have this support when you go with TensorFlow, because then it will be very difficult. So this support is here, and you have also some tools for optimization and debugging. And now for some people who want to touch the hardware. So this is how the Qualcomm Snapdragon looks like. Not exactly 680, but one of the previous one. And but it can still be shown. It's 2 centimeters by 2 centimeters, so not even inch by inch, but having inside billion, or if not more, transistors. More important here is to see what is the surface, what is the division, who takes more. You can see that this very good CPU takes just a small part of the surface. Much more is taken by the multimedia processing, and much more is taken by the GPU, and even the Hexagon is taking almost the same surface. So having seen that, why not try to utilize it? It is there. If you don't use it, you will only heat up this right up corner, and the rest will be just not used. And but before we check which hardware element we should use, let us try to understand how this machine learning calculation fit into the hardware components we have. We will do a small hardware software co-design analysis, but don't worry. This is the classical CPU. It's a typical workflow in a pipeline of CPU. Normal CPU have 20 stages. For simplicity, these are only 5 stages to show you how it works. So we have this instruction flowing from instruction fetch to instruction decode to then to execute the memory read and write back and all over again. Important here is that it is sequential nature. And the CPU is very efficient in executing such a different tasks, different calculation. It is, however, it's good for so-called task parallelism, but it is not good for the data parallelism. It means you have millions the same calculation, and then you have only 4 cores. It is the same like you have a traffic of 4,000 cars, and you have only 4 lanes highway. And each lane has to pass through 1,000 cars. So traffic jam is sure. Huh? And please look at the architecture of GPU as a contrast to the CPU. So CPU has normally 4 cores. GPU is equipped with few hundred or even few thousand of identical small cores. And they can perform several hundred or several thousand calculation in one cycle. So you have now 4,000 cars and you have 4,000 lanes. So even if it's slower than CPU, you will get much better performance. So GPU is perfect for our data parallelism. However, most of the time GPU is used for the rendering images because it's graphical processing unit. If you want, you can somehow accelerate the metrics calculation, which is used massively in a GPU. So we expect that GPU will be better than CPU. But next step in direction in parallel computing is so-called dedicated hardware, only to do this. And this is called Neural Processing Unit, or in our case, it's DSP, Digital Signal Processor. Our DSP has 2 512-bit vectors extensions, and this unit can perform up to 1,024-bit operation per single clock cycle. It means for us that we could, for example, have 64 additions of 2 8-bit numbers. 64 by 2 by 8 is 1,024. In case of 4 cores, you could only have 4 addition in one cycle. It means 16 times less. One can say, okay, they are 32 bits. Here are 8 bits. It's true, but in machine learning, we do not really need this 32-bit. 8-bit is enough. Huh? So therefore, we expect really to profit much from this dedicated hardware. We talk about data parallelism, but when is it possible? Here are 2 cases of simple addition, upper and lower, and 1 quiz question. Which addition can be done parallel and why? Why? Exactly. Thank you very much. That's a good question. Of course, the upper one, because these are 2 independent additions. So in lower case, we need the result of the first calculation to complete the second one. And it means that you cannot really do it in the same time if you want to have a good result. And in the machine learning, we get a lot of matrix calculations, and they are perfectly independent calculation. As an example, let's try to add 2 vectors like this, and you will see that this addition is independent, and you can have 5 person or 5 workers doing this addition like this, 1 plus 6, 2 plus 7, and then put it together. So it can be done in one turn. And this vector can be 1,000 or 1,000 by 1,000. It means that it is really parallel calculation and can be done together. To sum up this short hardware-software co-design, machine learning calculation should fit good into the GPU and DSP and not good to CPU. Are you curious what measurement, if the measurement confirms this theoretical analysis? I am, so sooner you will see it. But now we will talk short about the demo applications, and this app is normally following the pattern, where you can select the neural network model and runtime target. I mean, we may have different models in our application. So you may have inception, you may have mobile, there are several of them. You will be able to choose one of them. And then you can also choose different hardware components. You can work on it, just to compare. And then in the application, you will create, or we will create the tensor, input tensor, and by giving the input data, and then build this structure in the application memory, and then forward propagate this tensor. And in the end, we will have the so-called outcome tensor, and then we process this outcome tensor to get the probability. The highest probability will decide this is this class which we have. And in the meantime, we also measure time needed to perform this activity, just for the performance sake. So as you see, now we copy the model file to the resource, to the raw resource raw, and then this inception will be consumed by the app. Model will be populated, and so on. I would like now to do the demo. All right, so I told you that I have a script just for your information, how it looks like. I've created the data set which you saw with, and then just start running and showing you how effectively this is, because we've done it already. So these images are already created. Now it's fire up my GPU and checking the bottlenecks which are created. Normally it would take something like 1 minute. And then you should see that our GPU will fire up to start the training. You see there that the 4 GB, this is my GPU, is busy. It will be busy about half an hour to deliver yeah, it's a first step of training, and we have so-called cross entropy, which the program is minimizing. So when the cross entropy is close to 0, we can stop it, and then we say it's our measure, it's our loss, that it's okay. And then when the model is ready, we transform it to the Qualcomm model, and then using Android Studio, we can just compile the ready program and send it to the device, and then it should appear soon on the device, hopefully. It's just compiling. So now it is live. So we can direct this to the scanner and see that the probability that it's DS36 is more than 50%. Then we go to the printer. It's 100%. It's so obvious for him. And TC51 is also quite sure. With this one, we have more. Yeah, because it sees as well. But now you can see when you stay longer, it will adopt that it is TC75. Yeah? So this is the application which was developed. The first one. The second one is showing you the second project, where I told you that you will have a possibility to choose the model, and this model is chosen here, and you have a possibility to choose the CPU. First, we build the network here on the CPU, and we will see this quite a noisy. You see, this is noise. Huh? See the class here in the yellow. This is the upper is source. It means the good quality which we have. This one is also noise with a 99.99 probability. Huh? And you see that it takes something like 700 or even 1 second sometimes to do it. We can choose it now, the GPU, and build the network. It will take some time because it has to convert to DLC, but it's done already, 3 seconds. And now you can see other values, 300. So it is faster. And then we can choose, for example, DSP and build the network. And it is another. It's 70, 68. Yeah, so I want to switch to the presentation again. Okay, so in the end, let us talk about performance. So we saw that we had a different speed for the inference on CPU, GPU, and DSP. And to get more representative results, I measured time of 1,000 inferences on each hardware components. This demo will show you the result of running the same task on a different hardware component. So now you see we start with the CPU. It takes around 1 second. I waited until it finished 1,000 and then divided to see. And now we change it to the GPU, and with the GPU case, it takes to first initial, and then it comes faster. And in last we use DSP. That's the speed you have. Huh? All right. Another important metrics is the energy needed to measure this inference. Our goal is not only to make something fast, but also energy efficient. We have a mobile. It's not. It's only battery. So I used to measure software tool called RX Logger. It's our internal. Probably you heard about. It's RX Logger, and it's logging the current drawn from the battery, so you can easily estimate increase of power when you do while performing the task of image recognition. As we could see, the lowest performance was on CPU speed, as we expected, and we know why, because of this sequential nature. It does not fit just in the machine learning calculation. 2.5 times faster can the job be done on a GPU, but the fastest hardware is DSP 1111, even 11 times faster than CPU. And due to well-known fact of this vector processor and 8-bit calculation. And we still have a good performance accuracy. Even better, you can see it on this graph, this classification of 1,000 images. And equally interesting are the result of power drawn during inferencing. We can see that the GPU is fast, but also needs more power than CPU. The most power efficient is DSP because its architecture has only 8-bit calculations. Again, the same results shown as a chart with 92 watts when running DSP, 1.5 when running on GPU, and 1 to 2 watt when running on classical way on CPU. And finally, I estimated the energy which is needed to do this recognition of 1,000 images. I got this result by multiplying the additional power which is needed by the execution time. And we can see that due to the slow execution, CPU needs, in fact, the most energy. And the GPU, even if the power needed was higher because it was much faster, it consumes less energy. You have like 50%, half of the energy you save. And running inference on DSP is the most energy efficient, and so not only when executed faster, but also with the least power. I think this makes sense, having this data to try to have more, to have extra job which you have to do to send the job to DSP. And this is again the same graph showing you the energy consumption of 1,000 inferences. And in the end, lesson learned. So while implementing this project, first, try to define your case. And maybe you have already machine learning project in mind, and you would like to implement it. It could be something really simple. Improving some deficiency, solving a problem, or make something completely new. Let us know. We will try to help. We have infrastructure, we are building the Savannah, we are building devices, we are building also software around it. Let us know, we will look in this case. That's why I distributed these cards. If you can write your ideas and leave the contacts, we will definitely talk. When you already decide on the project, please take time to analyze before deciding for the machine learning approach. You know, it is the difficult and for many of us a new world. So it is important that you really think about that, maybe even try to find first the solution, as I said, the classical way, just to know the nature of the data, and then decide for the machine learning. Do not work alone. So try to build the team. Everybody was doing machine learning in this sessions was saying the same. I repeat, build a team. You will never have enough knowledge from machine learning, from data science, from Android development, and from the problem, because this is only a tool. And the problem, you need somebody who really knows the problem, like mechanical problems, like any problems you want to detect. So it is much better to have this network and in the team, these people, than to look for the answer in any Stack Overflow or whatever. Huh? So this is an important thing. You will need machine learning specialist, data science specialist, or somebody who wants to learn it as well. And then choose the proper machine learning framework, the one which you feel good, which is easy to understand, and which is good supported. Another thing, choose the hardware. You choose Zebra hardware. So if you have to now look and choose the software framework which this hardware is supporting, like I did, TensorFlow supported on Qualcomm. It's a good match, because you have support from either sides. And if possible, try to use first pre-trained models. It is going to save you a lot of time. Taking and collecting enough data, 1 million images, will take maybe years, and do it properly for people who start. So try to find a pre-trained model and just defreeze the last and try to do it fast. So even if the solution is not good in the beginning, your team, when the team sees that the application is working, it's delivering 60–70% of accuracy, it's already motivating enough, and then you can have possibility to make it better. So this is the idea. Yes, know the hardware. You can always run it on CPU, but if the hardware have a GPU and DSP, please use it. It will bring additional value added. In the end, document well your work. In our case, the first project was well documented. We didn't forget about it. And then it was really 1 or 2 days to make it easy available for the second project. You are going to profit from your knowledge, not today, but maybe in 1 month, or maybe in 1 year or 2 years. So this is really important. And that concludes my talk with, again, polite request. Please give us the feedback. We will be happy to listen from you about your machine learning projects, your experience. What you would like to do in the cloud with us using Savannah in the future? What would you like to do in our end devices? And we can have a good work together. Thank you.